Good morning, physics. How are you? I just wanted to continue our discussion from last time about standing waves. Just a quick reminder though, yes, it looks like these waves are staying in the same place, and that's why we call them standing waves, but they're not actually standing still. What's really happening is we have one wave going one way and one wave coming back the other way, but they're constructively or destructively interfering to make what looks like a standing wave. So since we're going to be doing some math today, I decided to get the whiteboard out. We want to talk a little bit more about standing waves, but I want to talk about something really unique about them. What's interesting about standing waves is anything can have a standing wave in it. Any material. At the start of this lesson, you had to watch the video of the dad in the swimming pool, and he made a standing wave. What happens is when he pushed down on the water, the wave went out, hit the edge, and then came back. And when it came back, it went back up, and then he pushed it down again. So he kept adding energy. If he had pushed at the wrong time, he would not have made a big standing wave. So the frequency matters, but it's a different frequency for whatever object it is that you're making a standing wave in. For today, we're going to use a slinky, and here's a video. It will be linked at the end if you want to watch the whole video. We're going to be watching a standing wave in a slinky. What's nice about the slinky is it's one-dimensional, so we don't have to worry about left and right or up and down. We just have to worry about going forward and backwards along the slinky. So when we find a frequency that produces a standing wave, we call that the resonant frequency. Okay, or we call it resonance. If you're a music person, you've heard that word before. We call it harmonic resonance when you're finding a frequency that matches the object that can produce a standing wave. So let's take a simple example. Let's look at the slinky, and let's look at just the simplest, the easiest resonant frequency, or the smallest or the easiest standing wave that you could make. It's going to look like this. Okay, and it's going to flip back and forth. It's going to go up, and then it's going to go down, and then it's going to go back up, and it's going to go back and forth between these two. The question you might be asking is, can we calculate the wavelength? Because we know V equals F lambda. So if I can find the wavelength lambda, let me draw a better lambda there. There we go. If I can find, that's worse. If I can find the wavelength, and if I know how fast the wave is going, then I can predict what frequency would produce this wave. So we start by finding the wavelength. So I'm going to call the length of the slinky lowercase l. That's the length of the slinky. We could measure that pretty easily with a measuring tape. And so what I want to do is I want to know what is the wavelength. Lambda equals question mark. So remember, a wave has to go up and then down. It has to have a peak and a trough to be a full wave. So this right here, is it a full wave? The answer is no, it's not a full wave. It's only half of a wave. Sometimes it's the top half, the peak, and sometimes it's the trough, but it can only be one or the other, and it goes back and forth between the two. So if I want to get a full wave, I'm going to draw this with dotted lines because it doesn't exist, but we can imagine it. The wave would have to continue past the edge of the slinky where that man is standing. It would have to go past him to get the full wave. So we've got a peak and a trough. So that is actually going to be exactly double the length. So lambda, and this is the biggest and simplest wave that we can make. So I'm going to call this lambda 1 because it's the first frequency that will produce a standing wave, and it is 2L. Okay, and then they raise the frequency and they find another standing wave, and this one is just a little bit more complex. It's got a peak and a trough, and it keeps alternating back and forth. So the part that's high goes low, and the part that's low that goes high, and this part right in the middle doesn't move at all. We call that a node. A part of the wave that doesn't move at all is called a node. The part that's moving a lot is called an antinode. And if you notice, we have a peak and we have a trough. So this lambda, I'll call it lambda 2, is just going to be the length of the slinky. That's one whole wave. This is a wave. Okay? Now let's go on to the next most difficult one. And I don't think they did a good job of it in this video, but it's when it's got 3 parts. So we've got a peak, a trough, and a peak over here, and these are constantly flipping back and forth. So lambda 3, well, we learned from this 2 examples, a full wave has 2 antinodes, one that's up and one that's down. So that's why this was only half of a wave, because it's either up or down, but it's not both. So this is a full wave right here. So a full wave is going to be this antinode plus this antinode. And then this one over here is just extra. So we actually have 1.5 waves in this one. So we only, if we want to measure just our first wave, we're going to just measure down to here. Okay? So that is, the third harmonic has 2.5 waves. But if this is 3 equal parts and we only need 2 of them to measure a wave, we don't need this last part to measure the wave. So this is going to be 2/3 of the string. Only 2/3 of the string are needed to make one wave. This extra piece is still there. We can't get rid of it, but it's not part of the first wave. It's actually half of the second wave. Okay, so we got 2/3 L, and you can imagine this goes on. We get to the fourth. We call these harmonics. This is the fourth harmonic. And we now have a peak, a trough, so that's 1 wave, a peak and a trough, that's 2 waves. So we actually have 2 full waves. So for the fourth one, we really just need half of the length of the string, or of the slinky. Okay, so far so good. Well, let's look at this pattern and see if we can write a general formula that works for all of them. I'm going to do a little trick here to make it so there's a more obvious pattern. Instead of 2L, I'm going to write 2L divided by 1. That doesn't matter if you divide by 1, it doesn't change anything. And this one, instead of being just L, I'm going to do 2 divided by 2L. Okay, 2 divided by 2 is 1, so it's still 1 times L, it's still L. So we didn't really change it, I just am writing it a different way. This one is 2/3 L, and this one's 1/2 L. Let me draw a better L. But instead of doing 1/2, what if I do 2/4? If you do the math, 2 divided by 4, we're still a half. I just wrote it out in a different way. And now you see a really clear pattern. For the first harmonic, it's 2L over 1. For the second harmonic, it's 2L over 2. For the third harmonic, it's 2L over 3. Do you see the pattern yet? So if I do lambda to the nth power, or to the nth harmonic, I should say, that's going to be 2L divided by n. Okay? 2 times the length divided by which harmonic we're on. So let's try it for the fifth harmonic. I'm running out of whiteboard space here, but I got 1, 2, 3, 4, 5. Oh man, that's almost a good drawing. Okay, so I've got 5 antinodes here. This is a fifth harmonic, and I just need this part. So I've got 1, 2, 3, 4, 5 even parts, but I just need these 2. So the fifth harmonic should be 2L over 5. Does that still follow our pattern over here? And it does. So that's a nice formula that we can use to figure out which wavelengths will make a standing wave in any object. And this is true for any object. It doesn't have to be a string. This is a Rubens tube. It works by pumping propane into the Rubens tube. The propane is then pushed out through these small holes, and on the ends we've got rubber gloves. They're flexible, so that way when we put a speaker on one end, the sound waves can leave the speaker and hit the glove and then transfer the sound waves into the tube. If we light the gas on fire, we can actually see the sound waves as they travel through the Rubens tube. Here we have a low frequency and we're panning up to a high frequency. Do you think we could use our equations from class to predict which frequencies are going to produce the best waves? Here's Mrs. Beck to explain to us how to do that.
Hey everybody, this COVID-19 thing is pretty weird, but here we are. We're going to learn some physics. So what we have here in front is called a Rubens tube. You're going to learn more about that in a second. But basically what we want to do is get the first harmonic frequency of this tube. And so we need to figure out what frequency of sound we want to shove through this tube so that it makes a nice standing wave. So we're going to have to do some math for that. We're going to start with this equation, which you will have just learned. This is the equation for wavelength and the length of a tube. And if we want to have a fundamental frequency, that means that n has to be 1, and when we plug that in, we get 2/1 times the length of the Ruben's tube. And as you can probably see, we are going to then get 2L. So the wavelength that we want to get as our harmonic frequency needs to be 2 of these. And we happen to know that the length of the Ruben's tube is 1.5 meters approximately. And so we're going to need to multiply that by 2, and we get about 3 meters. Awesome. So now we've got the wavelength. So sorry, that's the wavelength of the wave that we're talking about. And so now we get to do some more math. Yay! Okay, so now that we've got that wavelength, sorry, this is kind of gross, but hopefully you can still see it. Now that we have the wavelength, we can go back to our handy-dandy wave velocity equation, which looks like this. And we want to find the frequency of the fundamental frequency for this tube. So in order to do that, we're going to need to solve for f. So to do that, we will divide by wavelength on both sides. So now we've got the frequency is equal to the velocity of the sound wave divided by its wavelength. In this case, the velocity of sound through propane, which is what's happening here, there's propane gas going through this tube. The velocity of sound through propane is 258 meters per second. And we found out that our wavelength needs to be about 3 meters, which means that the frequency of this is going to be, I don't know, 260 divided by 3, what is that? This is
86?
Sure, yeah. Something along those lines. About 86 hertz. Anyway, so what we will now do is we will pump a frequency of 86 hertz through this tube, and hopefully it will give us a nice standing wave.
This is 86.6 hertz. How'd we do? Did you notice how this part is a little bit higher? That is the peak of the first wave. Off camera, we did it again for the second harmonic. This time we got 170, which is just about double what we got the first time. Now we're playing two frequencies that are just barely out of tune. Kind of interesting the way that they interact with each other. And that is a Ruben's tube. It's kind of a neat way to look at waves, isn't it? I guess there's only one thing left to do.